Okay, so that was a problem where we were just looking at the impulse acting on one object. The table was applying the impulse on the ball. Now let's go back to our collisions problem where we've got, say, two objects bouncing off each other, and let's use the fact that the forces that each exert on the other one are equal and opposite from Newton's third law. So what can we say about that? So let's imagine that we've got, say, an object 1 coming in, an object 2, they collide, they each apply forces on each other, say F12 and F21, and then they bounce off each other, or it's possible they could stick together or something, but whatever, the forces stop interacting with each other and they somehow move off. So let's use the idea that these forces are equal and opposite. Now, we know that J12, in other words, the impulse that object 2 exerts on object 1 is equal to the change in the momentum of object 1. In other words, P1 final minus P1 initial. And then we know that the impulse 210, in other words, the impulse that object 1 exerts on object 2 is the change in the momentum of object 2. In other words, this is P2 final minus P2 initial. Now, let's add these two equations together. We'll just add the left sides, add the right sides. What do we get? So on the left, we get J12 plus J21 equals, and then on the right side, P1 final minus P1 initial plus P2 final minus P2 initial. Now, what is J12 plus J21? Well, remember, these are equal and opposite. If they're equal and opposite and we add them together, we get 0. So the sum of the impulses, the two impulses, the impulse that object 1 exerts on object 2 and the impulse that object 2 exerts on object 1, they are equal and opposite. So adding them together gives us 0. Now, let's take the negative terms. Let's say this one, and let's bring them to the other side. And what do we get? So, we get P1 final plus P2 final equals, now these coming to the other side, we get, this is negative and negative, so they'll be positive P1 initial plus P2 initial. There we go. Well, let's look at this. Notice we've got P1, P2 added together finally, and P1, P2 added together initially. So we've got, again, the same kind of quantity evaluated on both sides, on the left side and the right side, but one of them is evaluated finally, and the other one is evaluated initially. Well, if we add both momenta, so the momentum of, it's just as an aside. When we talk about the momentum of one object, we say one momentum. If we've got more than one, we say momenta, not momentums, momenta. So, when we add the two momenta together, that's the total momentum. So if we've got two objects, and we add each momentum, we're talking about the total momentum of the whole thing. We're just adding the momenta of each object, the momentum of each object, to get the total momentum. So we'll write that the momentum of object 1 plus the momentum of object 2, that is the total momentum. The total momentum of the system, if we've just got two objects in the system. We might write this as P total, or we might just not write the subscript at all and just keep in mind that's what we mean. We mean the total momentum. So what is this telling us? It's telling us that the total final momentum equals the total initial momentum. This is an incredibly important result. Let's just remember what this is saying. Let's go back and remember what kind of assumptions we made in order to get here. We are talking about two objects that are colliding together, but we had to make the assumption that we were ignoring all other forces acting on the objects other than the interacting forces. So whatever forces each object exerts on the other. We had to ignore anything else, like the gravity of the Earth or air resistance or anything like that. So we call that an isolated system. We're talking about just these two objects and what forces they are exerting on each other. We refer to it as an isolated system, isolated from anything else that might be exerting forces on them. So for an isolated system, as long as we're only talking about the forces in between each other, what one acts on the other and what one acts on two, what two applies on one, the final momentum of both objects added together is equal to the initial momentum, total momentum, of both objects added together. This is so important that it's got its own name for this result. This idea is called Principle of Conservation of Linear Momentum. And what it states is the total linear momentum of an isolated system remains constant. In other words, it does not change. Now let's remember, what do we mean by an isolated system? We mean a system of objects. Now we've been talking about, say, two objects colliding, but you could have three or four or more or even just one. An isolated system means that we're ignoring all external forces that are acting on the system, acting on any of the bodies in the system. The only forces we're considering are forces between the objects, forces that one object exerts on one of the other objects. That's an isolated system. As long as we have an isolated system, the total linear momentum, in other words, the sum of the momenta of all of the objects, in other words, say P1 plus P2 plus P3 plus P4, as many as we have, that sum always remains constant. It does not change. This is a very, very amazing result. So this means, remember, that if we've got two objects with some total initial momentum, the momentum of one plus the momentum of another, and they collide, during that collision, the forces that are being exerted on each, one force might change the momentum of one object, because it's, say, in one direction, it changes the momentum one way, but the other object exerts an opposite force on this one, and so whatever change in the momentum of this object will be in the other direction. And so the changes in the momentum, because of the forces being equal and opposite, the changes in the momenta are equal and opposite. So whatever momentum we have to begin with in total is the same as the total momentum we end up with. Let's stick some numbers in here. Okay, let's imagine we've got two train cars. We've got one train car with a mass of 65 times 10 to the third kilograms. And another train car with a mass of 92 times 10 to the 3 kilograms. Let's say this one is moving to the right at 1.30 meters per second. And this one is moving to the right at 0.800 meters per second. And let's imagine these two train cars are going to hitch up and move off together, but let's just look at the initial situation to begin with. Let's call this one Object 1, and this one Object 2. Let's figure out what the momentum of each is and then add them together, and we'll get the total final momentum. Now this is just a one-dimensional problem, so we'll just define the horizontal direction as our x-axis, and we'll say positive is to the right. Now, is this an isolated system? Well, there are other forces acting on it. There's going to be gravity pulling it down. There's going to be a normal force pushing up. Now, in this case, while there are other forces acting on them, we know that those are not going to be changing the momentum of the object because they cancel each other out. The weight of each is going to be canceled by the normal force acting on each, and so they cancel out. The only forces actually affecting the momenta of the two objects will be the interacting forces between them. So, even though there are other forces acting on the objects, we can treat this like an isolated system. So what is our initial momentum of object 1? So we'll call this P1 initial. Well, it's going to be m times v. In other words, 65 times 10 to the 3 kilograms times 1.30 meters per second. And then what is the initial momentum of our second object, P2 initial? That's going to be its mass times the velocity. So that is 92.0 times 10 to the 3 kilograms times 0.800 meters per second. Now, if we want to write this as a vector equation, we can say that P1 initial, that's in the x direction, so x hat. P2 initial, that is also in the x direction, so x hat. Then, multiplying these out, add them together, what do we have? We have that our total initial momentum, the sum of these, is then equal to 1.58 times 10 to the 5th kilogram meters per second, and that also is going to be then in the x direction. There we go. So there is our total initial momentum. Now, what's going to happen? These two trains are going to collide together. They're going to move off together at the same speed. Let's see if we can figure out what is that final speed. So here we have both trains moving off in the same direction at some similar final speed. Let's figure out what the final total momentum is. So we have P1 final is equal to same mass, 65 times 10 to the 3 kilograms, times, what's the speed of train car 1? Well, V final. And again, that's in the x hat direction. And what is P2 final? That's going to be the mass of train car 2, 92, times 10 to the 3 kilograms, times V final. And again, in the x hat direction. Adding those together, our total final momentum is then 1.57 times 10 to the 5th kilograms times V final, and again, that's in the x hat direction, so we have x hat. Now let's use the principle of conservation of linear momentum, and that tells us what? That tells us that our initial momentum must equal our final momentum. So we'll equate those together, and what do we get? We get 1.58 times 10 to the 5th kilogram meters per second x hat equals 1.57 times 10 to the 5th kilograms times V final x hat. And then we can divide both sides. This is all in the x hat direction, so we don't have to worry about that. We can divide off the 1.57 times 10 to the 5th kilograms. V final is then 1.58 times 10 to the 5th kilogram meters per second divided by 1.57 times 10 to the 5th kilograms, and we end up with a final result of V final is equal to 1.01 meters per second. And there we go. The cars end off moving to the right at 1.01 meters per second. Very, very good. Now, I've got a problem for you to try. Let's imagine we have a similar setup here with the two trains, but The train on the right, let's imagine, is not moving to the right. Let's imagine it's actually moving to the left. How would that change the problem? Well, over here, when we find the initial momentum of object 2 of the second train car, it's going to the left, so how would that change the initial momentum? It would be what? It would be negative. So this would be negative. You'd add these together, you'd get a different quantity here. Down here, you'd go through this. What would you get? How would you, what kind of answer would you get? Well, see if you can figure this out. It turns out that your final speed would actually be 0.0694 meters per second. See if you get that result. So, very, very important result to keep in mind, or something to keep in mind, is that when you're breaking things down into components, remember, anything going in the same direction as x hat will be a positive value, but if it's moving in the opposite direction, say in the left in this case, it has a negative momentum, or it's in the negative direction. Okay? So, try and keep that in mind. Now, we can actually classify collisions into two very broad general types. There's one where the kinetic energy is conserved. This type of collision we call an elastic collision. These are where the kinetic energy is conserved. Collisions where the kinetic energy is not conserved, these are called inelastic collisions, or it's an inelastic collision. So keep in mind, for elastic collisions, the kinetic energy is conserved. For inelastic collisions, kinetic energy is not conserved. Now, for which one is the momentum conserved? Both of them. All of them. As long as there are no external forces, as long as it's an isolated system, or, like we saw in the numerical problem, as long as the external forces cancel out or can be ignored, the momentum is conserved. Always. But sometimes the kinetic energy is not conserved. Now, this has to do with the objects that are actually colliding with each other. What kind of objects are they? If they're very, very hard objects, maybe like two rock balls or something like that, or maybe two steel balls that will not deform very much, they tend to conserve much of the kinetic energy. However, if you have two objects like two pieces of sticky putty or something like that, or the train car problem that we've just looked at, when they come together, if they stick together or if they deform a lot permanently, then that takes some of that kinetic energy and converts it into the work that's required to deform the objects and maybe hold them together, that sticks them together, that takes energy out of the system and turns it into thermal energy, typically heat energy, which then removes it from the kinetic energy, so the objects end up with less kinetic energy than they started with. So the ones that bounce off each other, like very hard balls, steel balls, or pool balls or something like that, those are much closer to conserving the kinetic energy, being elastic collisions. Objects that deform and stick together, those are going to make inelastic collisions. Now, when the two objects actually come together and do stick together and then move off as a single object, those lose the most amount of kinetic energy, and those are called maximally inelastic collisions. So anytime you've got them sticking together, they are losing as much kinetic energy as possible. They will still typically move off together. They're not going to come along and stick and just stop unless the total initial momentum was zero to begin with. Because remember, momentum has to be conserved, and if there was any initial momentum, total momentum, they're going to have some total final momentum. However, if the momentum of one is the opposite of the momentum of the other, when they come together and they stick, they'll end up with zero final momentum, and they'll just stop and stay where they are. So remember, momentum still has to be conserved. Now let's take a look at a very, very general problem. We won't put any numbers in, we'll just look at variables, but we'll get some very interesting results. Let's see.